Hi everyone. In this video, we will explore some additional properties of derivatives that follow from the mean value theorem, which we proved earlier, and also from some theorems that we will prove today. So to begin with, we want to look at another formulation of the mean value theorem. This is called Cauchy's mean value theorem. It says, suppose f and g, which are functions mapping the interval ab into R, are continuous on AB and differentiable on the open interval AB. Then there exists a point C in the open interval AB such that f prime of C times g of B minus g of A is equal to g prime of C times f of B minus f of A. Further, if g of A is not equal to g of B and g prime of C is not equal to 0, then f prime of C divided by g prime of C is equal to f of B minus f of A over g of B minus g of A. Now, to sort of make sense of this, I think it's easiest to think of this as being a theorem about parametrically defined curves. So imagine you have some parametrically defined curve in the plane. So I'm going to call this R of t, whose x-coordinate is the function g of t and y-coordinate is the function f of t. So if we were to plot that function in the plane, right, we would get some curve. But again, even though f and g are functions now, this curve need not define the y-coordinate as a function of the x-coordinate. So, we can have all sorts of things going on here. So in this formulation, and particularly if I look at this formulation here, okay, really what this is saying is, if I look at 2 points on this curve, so you can sort of imagine the curve is parameterized, maybe, so we're moving this way along the curve, okay? So at some value A, here is R of A, and that would just be the point G of A, comma, F of A. And over here at some other point, maybe here, this is R of B. Okay, but of course, R of B would just be the point G of B, comma, F of B. Okay. Now, consider the line segment that connects these 2 points. Okay, this line segment has slope f of B minus f of A over G of B minus G of A. Now, so on the right-hand side, this then is really just the slope of this line. Now, this quotient here, right, really expresses, so if I asked, what's the slope of the tangent line to R of t at any point, it would be dy dt over dx dt, or in this case, f prime of t over g prime of t. So on the left-hand side, what we really have is the slope of the tangent line at any point along this curve. Okay, so what this is saying is there's some point C between A and B, so that essentially at some point along here, and maybe if I sort of look at this for a minute, maybe it's this point here, maybe this is C, so that if I take the tangent line at this to the curve at this point C, right, I get that R prime of C here would just be G prime of T. So I shouldn't really call this R prime of C. But the slope of this line, right, would be F prime of C over G prime of C, assuming that this is the point R of C. Okay. So again, it's like the mean value of Lagrange's mean value theorem that we saw before, but you can think of this as being something about like a mean value theorem for parametrically defined functions in the plane. Now, as we'll see, this has other important uses that aren't just about parametrically defined curves in the plane, but this is sort of one way to realize this theorem. Now, I also just want to quickly point out, if we can prove this first part, then the second part actually follows almost immediately from that, right? Because if I take that first equation, if I take this equation, and if g of a is not equal to g of b, then this term g of b minus g of a is not zero. And since it's not zero, I can divide both sides by that. And if g prime of c is not zero, then I can divide both sides by g prime of c. And this is just the transformed version of that earlier equation, right? So, it turns out here that this second piece of the theorem is just an immediate consequence of the first. So, if we want to prove this full mean value theorem, we really only need to prove this statement here, and then the second would follow almost immediately. Let's prove it, and we're sort of just going to sketch the proof. It's actually very similar to the proof of Lagrange's mean value theorem in that we're going to construct an auxiliary function. We're going to apply Rolle's theorem to that auxiliary function, and then the result will just fall out. Okay, so we're going to define a function. We're going to call this function psi. Just going to map from AB into R. And we're going to define it as follows. Psi of x is going to be equal to f of x times g of b minus g of a minus g of x times f of b minus f. Let's fix that. F of b minus f of a. Okay. Now, in doing this, we can quickly check that psi satisfies the properties we need. So in particular, psi is continuous on AB. Why? Well, f and g are both continuous on the closed interval AB. These values are constants, right? So this is just a constant times f minus a constant times g. So psi will be continuous by the algebra of continuous functions. Similarly, psi will be differentiable on the open interval by the algebra of differentiable functions. Again, f and g are both differentiable on the open interval AB. These are constants. So psi will be differentiable. And the last thing that is not super tricky to check, but that we need to check, is that psi of A is equal to psi of B. So we plug A in here for X, right? Then the first thing to notice is that we will end up with a G of A, F of A, and that'll be positive. Here we'll end up with a negative G of A, F of A. And so all we'll end up with at the end is F of A, G of B, minus G of A, F of B. And we can actually check that if we plug in B, the same thing happens. So if we plug in B, then I get a F of B, G of B, minus a G of B, F of B. So those will cancel out. And the only things I'll be left with are going to be a F of A, G of B, minus over here a G of A, F of B. So again, just checking the algebra there, I get this. So I can apply Rolle's theorem. Okay. So hence, by Rolle's theorem, there exists a C in the open interval AB such that psi prime of C is equal to 0. Well, okay, what's psi prime? That's just F prime here, that's a constant, minus a G prime here. So psi prime is just psi prime of C is F prime of C times g of b minus g of a minus g prime of c times f of b minus f of a, and that is psi prime, so that of c, so that's equal to 0. And so again, what do I want here? I just want to move this term then to the other side. So, and hence f prime of c, g of b minus g of a is equal to g prime of c times f of b minus f of a. Okay, and that concludes our proof. Again, that concludes this. This is just some algebra to get to an alternate representation under some specific conditions. Okay, so Cauchy's mean value theorem proof is really very similar to Lagrange. In spirit is a similar result, although it's a slightly different characterization that, as we'll see in our next proof, is very helpful to have sometimes. All right. So with Cauchy's mean value theorem at our disposal, we want to go back and look at a result that is used quite a bit in Calculus 1 that we can now prove with Cauchy's mean value theorem. So we're going to start by stating the theorem. We'll look at an example to sort of remind ourselves how this worked in, say, a Calc 1 course and to sort of see how the theorem works in practice. And then we'll spend a good bit of time proving the theorem. So the theorem is what's more commonly called in a calculus course L'Hopital's rule. So the theorem says, suppose f and g are continuous on the closed interval AB and differentiable on the open interval AB. Further, suppose that for some point x naught in the open interval AB, the limit as x approaches x naught of f of x is 0, and the limit as x approaches x naught of g of x is equal to 0, and g prime is non-zero on a neighborhood of x naught. Then, if the limit as x approaches x naught of f prime of x over g prime of x is equal to some finite real number L, then the limit as x approaches x naught of f of x over g of x is equal to some value L. So let's remind ourselves just, how do we use this in, say, a Calc 1 course? So usually you might be asked to, say, evaluate something like the limit as x goes to 0 of sine of x over x. Okay. So if we look at this function is continuous and differentiable on all of R. This function is continuous and differentiable on all of R. So you can make A and B whatever you want, but let's make it some interval that contains 0, right? So let's say like minus 10 to 10, right? So continuous and differentiable on minus 10 to 10, okay? Further, we'll suppose that for, so our x naught is 0, and notice that the limit of the top is 0. Limit of the bottom as x goes to 0 is 0. And we want to make sure if I look at the derivative of this, the derivative of this is just 1. So it's non-zero on a neighborhood of x naught. Okay. All right. Now what this says is if the limit of derivative of the top over the derivative of the bottom exists and is equal to some number, then the derivative of this original function must be equal to that same number. Now, typically in a Calc 1 course, right, we would write, and maybe I'll write this in a different color because this is sort of fine in a Calc 1 course, but we'd often, without thinking much about it, just go, well, this is equal to this. Okay. Now, in this case, it is, but I want to emphasize that at this point, I don't know that these are equal because I don't yet know that this limit exists. Okay. Now, I can then look at this is certainly equal to this is just algebra, right? And cosine is a continuous function. So I can just plug in 0 and that'll give me 1. Now, since I know this limit exists, I now know that this limit exists and must also be equal to this. Okay, so this first, some folks will even have people like you write like it equals with a question mark, like maybe this will work, right? But I need to come back at the end, right? Now that I know this limit exists and is equal to 1 now, okay, yes, these two things are in fact equal. But I don't know these are equal until I know that this limit exists formally, right? That's what L'Hopital's rule says. Okay. Now, um, this is a fairly straightforward case. You might have learned, well, you can use L'Hopital's rule on lots of different kinds of indeterminate forms. So you can do it when you have a limit of the form infinity over infinity, other things. We're dealing with the problem where we have a finite value we're taking the limit at. So our x naught is some finite number, and also the limit itself is some finite value. But once you have this, a lot of the other cases you can sort of extend to by making some clever sorts of substitutions. So we'll stick with this case for the time being. So what we want to do is prove this theorem. All right. Now this is going to take a bit of room, so let's clear the board a bit here. All right. So to start with, let me note that our assumptions were what? That the limit as x approaches x naught of f of x is equal to 0, and the limit as x approaches x naught of g of x is equal to 0. We also assumed that f and g were continuous on the whole interval AB, but in particular at x naught. So that means that a consequence of those two things is that f of x naught and f and g of x naught are both 0 because they're continuous at 0. So at x naught. So since the limit at x naught is 0 and the function is continuous, the function values must also be 0. Okay. Now, since G prime, and let me emphasize, in the statement of the theorem, there's actually a typo in the book. The book says that the function, you want to assume the function G is non-zero in a neighborhood of x naught. That should be G prime. In the one I put up here on the screen, it's correct, but in the book, there is a typo. It should be G prime is non-zero on a neighborhood of x naught. So since G prime is non-zero on a neighborhood of x naught, what I'm going to do is I'm going to choose a delta greater than 0 such that G prime of x is not equal to 0 for all x in the interval x naught minus delta to x naught plus delta. Right? This is just what it means for G prime to be non-zero on some neighborhood, right? I can choose some little ball around x naught so that G prime of any x value in that little ball will not be 0. Okay. All right. Now, then for any x, in this delta ball around x naught, other than at, let me, so for any x in this up to x naught union x naught up to x naught plus delta. Okay, so basically for any x in this neighborhood, but delete x naught. So for any x in this neighborhood other than x naught, G prime, sorry, G of x, not G prime of x. G of x cannot be 0. So think about why that's the case. So in this neighborhood, right, my derivative is never zero. Okay, so at x naught, my function g is 0. And I have some neighborhood of x naught where my derivative is never 0. If my g came back at some point to be 0 again, well, then by Rolle's theorem, I'd have to have a place in between where the derivative is 0, but that never happens. Okay, so by Rolle's theorem, it really is how I know this. But the other way to think about it is right, the derivative would have to be 0 at some point for me to turn and come back down to the value of 0. So my g of x is never 0 in that interval. All right. Trying to make sure I have everything carefully set up here. I have my notes here to make sure we get everything perfectly laid out. All right. So now take an arbitrary x value in x naught minus delta to x naught union x naught up to x naught plus delta. Okay. And without loss of generality, let your x value be greater than x naught. So in general, we want to take some x near x naught, but not at x naught. And without loss of generality, let's just assume x is bigger than x naught. If x is smaller than x naught, then you'll see how we could deal with that. But let's just assume we're in this upper interval, okay, this upper half of the delta neighborhood. All right. So now what I want to check here is that we satisfy the conditions for Cauchy's mean value theorem. Okay. So note that I'm going to look on the interval x naught up to x. So f and g are continuous on the interval x naught up to x. F and g are differentiable on x naught up to x. Oh, sorry, that should be the open interval. And how do I know this is true? Right? F and G, I'm assuming, are continuous on the whole interval AB, right? This is a subset of that interval. Same thing here, subset of AB. So we're all set there. Okay. Notice that G prime of x is not equal to 0 on, in this case, x naught up to x. And if I look at g of x minus g of x naught, okay, and sorry here, I should not use x here. X is going to be an arbitrary value in there. So let's say g prime of t is not equal to 0 on this interval. And now g of x, I'm looking at the specific x value that I've chosen earlier here. This is not equal to 0. Well, sorry, it's equal to g of x, right? Because g of x naught is 0. And this is not 0, right, from up here, right? Okay. So all those hypotheses, not just of Cauchy's mean value theorem, but of the special version at the bottom apply, okay? And so by Cauchy's mean value theorem, there exists a C in the interval from x naught up to x such that f prime of C over g prime of C is equal to f of x minus f of x naught over g of x minus g of x naught. But again, remember, right, f of x naught and g of x naught are both 0, so this is really f of x over g of x. Okay. Now, I want to emphasize that this C value, right, this C value depends on what your X is that you chose up here, right? If you had picked a different X, right, an X that was maybe a little bit closer to X naught, then your C value would necessarily change. So it might, in a minute, I'm going to start calling these C sub X, right, just to emphasize that that C value depends on X. But for the time being, right, for every X value satisfying these conditions, right, essentially this condition is that it's close to X naught, and I'm just assuming that it's bigger than X naught, this works. You can go ahead and notice if you took an X less than X naught, you would just flip the order of these X and X naught things, but everything would still work out the same so far. Okay. All right. So let's keep going. All right. So to summarize, so for each each X, there exists C sub X in the interval from X naught up to X, such that, and again, just summarizing that last line, we have f of x over g of x is equal to f prime of c of x over g prime of c of x. Now, what we want to do is we now want to take a limit of both sides as x approaches x naught. Okay. So, taking x to x naught, we have, okay, what happens here? So, on the left-hand side, I have the limit as x approaches x naught of f of x over g of x. Okay, and that's going to be equal to the limit as x approaches x naught of f prime of c sub x over g prime of c sub x. Well, let's think about what's happening as x goes to x naught. Okay, so what's happening? This interval is collapsing. And c sub x, right, which is changing for every x, but it's trapped between x naught and x. So you can sort of imagine, right, you have x naught here, you have x here, and you have c sub x trapped somewhere in between. But now you're taking x to x naught. As this x squishes down towards x naught, the c sub x is trapped in the middle. C sub x must also be going to x naught. Okay, so taking x to x naught is the same as taking the input here to x naught. So this is the same as the limit as x approaches x naught of f prime of x over g prime of x. Okay, and now notice here, now we are assuming, right, our assumption is that this exists. So this must also exist and be equal to this value, which is what we wanted for L'Hopital's rule. Okay. So Cauchy's mean value theorem helps us significantly sort of in this crucial step of approximating f of x over g of x by f prime of some value over g prime of some value. And then in the limit, we're able to recover the exact result that we want. Okay. All right. So again, L'Hopital's rule is a very handy theorem for actually computing computing derivatives, computing limits by hand. So now we want to look at one final theorem, and we're not going to prove this theorem. The proof is in the book. It's fairly straightforward, so I would encourage you to go read the proof and understand it. But I actually just want to spend a bit of time talking about this theorem, and in particular, sort of its consequences for derivatives. So this theorem is called Darboux's intermediate value theorem for derivatives. I've alluded to this earlier, and we'll talk about that a bit more in a second. But just for the statement of the theorem says if f is differentiable on the closed interval AB, and if k is some number between f prime of A and f prime of B, then there exists some value c between A and B such that f prime of C is equal to k. Now, what's this theorem saying? So visually, right, we could think about, okay, we have some function, it's differentiable on some interval AB. Maybe here's A, here's B. I can calculate the derivative here, right, at some positive number, and calculate the derivative over here. It's some negative number, okay? So the slope of this is f prime of A. The slope of this line is f prime of B, right? And now if you pick any slope between f prime of A and f prime of B, for example, in this case, it's easy to see 0 would be one such spot, right? There must be some point in between, at least one point, where the derivative is 0, okay? So this is like an intermediate value theorem, but instead of talking about the values of the function, it's talking about the values of the derivative of the function, okay? Now notice that all we're claiming here is that f is differentiable on the closed interval AB. That does not mean that the derivative function is necessarily continuous, right? So we saw in a previous video, if you look at the function f of x is equal to x squared sine of 1 over x for x not equal to 0, and 0 when x is equal to 0. This function is differentiable on all of R, as a matter of fact, and f prime of x is 0 when x is 0, and otherwise it is x squared, sorry, it's 2x sine of 1 over x, and you end up getting a minus cosine 1 over x here when x is not equal to 0. So this function is differentiable for every real value of x, but this function f prime is not continuous at 0, right? So in particular here, the limit as x goes to 0 of f prime of x actually doesn't exist. Okay, you have here this term is going to 0, but this term has a oscillatory discontinuity at 0. So the limit actually doesn't exist. So this function is not continuous at 0. Now, of course, if this function f prime were continuous, then the original intermediate value theorem would suggest that this has to be true. But what this is saying is it doesn't matter whether your derivative function is continuous or not. Just the fact that it's a derivative function means that it must satisfy this intermediate value property. Okay. Now, that's actually sort of a powerful thing. And in some ways, what it's saying is, okay, yeah, functions that are differentiable everywhere may not have continuous derivatives, but they still have to have some of the nice properties that continuous functions have, like this intermediate value property. Now, And you can note here, right, if I were to sort of try to draw, well, I draw the graph of the original function f here, right, you can see that even though, again, we've already seen its derivative is not continuous, we can still see or try to justify why the graph must have uh, this intermediate value property, the derivative must. So, right, this is oscillating between -1 and 1, and the oscillations go infinitely fast here near the origin, and then smooth out over here. All right. If we look at this, as we get close to 0, we have infinitely steep derivatives, right? So like if I just look at this, as I get close to 0, right? So the values of my derivative, uh, let's see, this is going to be small as I get close to 0. Actually, sorry, they're going to be, they're not going to get, the derivatives themselves aren't going to get infinitely large. They'll be bounded by, let's see, this is some sort of optimization problem. They'll be bounded, okay? But even though they're bounded, you're switching back and forth between the largest one and the smallest one infinitely often, right? As you get closer and closer and closer. So if you were to pick two values, say on either side of 0, right, and look at the derivatives at those points, your derivative must pass every value between those. Your derivative is still sort of varying in a nice way, even though it's not varying continuously necessarily. It's still hitting every value in between. All right. So what is the big sort of conclusion of all this? So one consequence of this theorem then is that a derivative function, as in that theorem, so again, I want to emphasize it requires that the function be differentiable on a closed interval. Okay, but if you have a function that's differentiable on a closed interval, then the derivative cannot have discontinuities of the first kind. It can only have discontinuities of the second kind. Now, when we say discontinuities of the first kind, discontinuities of the first kind are removable discontinuities or jump discontinuities. Okay. It can only have discontinuities of the second kind, and discontinuities of the second kind, right? Those would be oscillatory or infinite discontinuities. Okay. So the derivative cannot have a jump discontinuity, because if you had a function, like imagine you had a function and you thought the derivative was this. Imagine this is -1 and this is 1. You cannot have a function that has this as its derivative. Now, you might say, wait, Quinn, that looks like, isn't that the derivative of absolute value? Okay. Almost, but not quite, right? I've colored in this circle here, right? The assumption is that the function is differentiable on the entire closed interval. This is not differentiable at 0, so it's not differentiable on any closed interval containing 0, right? So so the derivative of this would be this with an open circle down here, okay? There is no function that has this as its derivative, right? It's just an impossibility. This does not have a intermediate value property because, for example, there's no place where the derivative hits 0. Okay. So this is, I like sort of, finishing up at least a discussion of first derivatives with this because it sort of tells you that derivative functions, again, you can have a function that's differentiable everywhere, and that derivative is not continuous. But this gives you some hope that it can't be too badly behaved, right? That it still must have some nicer properties than you would expect from just a random function that you pulled out of a hat. So this concludes our discussion of the first derivative. In the next video, we'll look at higher order derivatives, really with an eye towards thinking about Taylor's theorem and Taylor polynomials and Taylor series. We will revisit those topics later on when we talk more about Taylor series later in the course, but we want to at least start thinking about higher order derivatives and some of the information that they give us about a function. Once we conclude that, we will then begin discussing integration, which we'll spend several weeks covering before we move into the sequences and series material for the end of the course.